So we are here today to attend the talk by Elena-Ioana. Dr. Elena is a researcher with CNRS in TIMA labs in Grenoble, France. She received a PhD in electronic engineering with a distinction from Universitat Politécnica de Catalunya in Spain in 2011. She has been involved in several European projects and national projects. She has served on the technical program committees and organizing committees of conference and symposium in design automation test domains, including DATE as topic chair and IEEE ETS as program chair. She's a reviewer, guest editor, and associate editor of several international journals. Her main research interests are on reliability and robustness assessment, design for reliability, test strategy, and security primitives for CMOS and beyond CMOS RAMs in traditional and non-von Neumann computing, neuromorphic, and CIM paradigm. So thank you very much, Ioana, to accept our invitation. And it's a great pleasure for us to have your talk today in a very interesting and hot topic. So the floor is with you to start the presentation.
Thank you, Ricardo, for the introduction and for the invitation. It's a great pleasure for me also to be here and to talk to you about emerging memory technologies. Now, well, when I talk about emerging memory technologies, there is a lot of debate now if they are still emergent or they are already prototypal. So, but still the language is on emerging memory technologies today. So I want to have a discussion with you if their versatility, so the fact that they are very widespread both in technology and application, is it good for us or is it problematic? So this is what I'm going to talk to you about today, and I'm going to place my talk in the context of architecture, system, and application, where we see today that we have a lot of variety in what we require from our electronic systems, and this variety translates in what are the properties we most search in our system, and these properties need to be carried up by the device. So with this, I would like to say that in order to build a smart future, we need to base ourselves on the new technologies and the devices that come with it, but also we need to build up from architecture, system, and application in such a way that we can take advantage or the most benefit of what we can from technology, device, and from architectures and systems. So if we look at this context today, what we see from the technology and device side, we are basing on technology which can be CMOS or otherwise. Based on this technology, we are fabricating devices which might have fabrication and process issues. Based on this, we could build fault modeling and fault tolerance and security for our circuits, and then this one brings us up to the circuit design. Now, when we look from the top down, where we look from architecture, system, and application, we know that we want to have, today we are looking for smart systems that can compute by themselves, that can evaluate and predict by themselves. So all these smart systems are based on computing architectures, which also are built on circuit design. What it is on the middle of all this is the memory. Why is the memory? Well, it's because it occupies the largest area on the chip. So it is the circuit component that most affects the behavior of our systems, and also is the first circuit component that is ported to a new technology, because it's very regular and because we always have very strict requirements on our memory. We want it to be small, we want it to be compact, we want it to carry as much data as possible, we want it to be low power, we want it to be reliable, we want it to be secure. So all the strong requirements are put on our memory devices. Now, what is the problem with today's memories is that we are kind of reaching the CMOS technology limit, and we are hearing that for many years now. So because we are hearing that for many years now, we are preparing to look into the future and go beyond CMOS technologies with other technologies like the resistive ones that I'm going to talk to you about today. And another problem with today's memories is the memory wall. So we are actually facing a problem with the memories in the sense that the effort required to bring data back and forth from the memory to the application, it's actually overthrowing everything else in the system. So we consume a lot of power for this data manipulation. We incur a lot of latency because of this data manipulation. We are hitting our system. We are making our system slow. So these main issues, the CMOS technology limit and the memory wall, when we talk about memory system, has actually brought us in the research direction that I'm going to present today, which is the one of new technologies. So to kind of mitigate the technology problem, the CMOS technology problem, we are looking into emerging technologies which are based on novel materials and novel fabrication steps, which actually bring us to novel circuit designs. In order to fix the memory wall, there are many proposals on how to change architectures. So we are going from von Neumann architectures, where we have a strict separation in between memory and processing elements, to non-von Neumann architectures like in-memory computing or neuromorphic computing, where we are trying to do computation where the data resides, so within memory, in such a way that we mitigate all those issues inquired by data manipulation from memory to the processors. All this is happening in the context of new applications like smart sensors, IoT, medical diagnostics, smart cards, and so on. So I'm not saying that all these are new applications, but they are applications with new features. Every day, every year, we are adding new features to these smart sensors, smart IoT, medical diagnosis. So all this is actually going down to new circuit designs and new technologies. So in this context, I like to show this slide because it's very talkative. It's actually a comparison between what happens to the new device and materials and what happens to the new architectures and packaging. And if we put all this together, we actually manage to get more efficiency out of our system. So this is an image from 2015. It seems like it's dating, but actually everything that it's in here, it's true today. And we are on the way of actually realizing this great improvement in the system operation, in system latency, in system power consumption, in accuracy of computations with neuromorphic computing, quantum computing, analog, approximate computing. So my talk today actually is going to be on the new devices and materials side. I'm going to focus a little bit on the spintronic devices and memoristive devices that are bringing us the neuromorphic analog computing, also approximate computing in memory computing, and are actually helping us to evolve in the direction desired. So the outline of my talk is to underline and explain a little bit what happened to the good old RAMs, why we are kind of moving away from SRAM, DRAM, and even flash memories, why we don't, well, we do work a lot into improving them, but why we are looking into alternatives for these devices. Then I'm going to show you which are the alternatives of these devices, which are the new resistive RAMs that are being included in the market. And then I'm going to show you how versatile they are, because there are many technologies with many applications, so they have a very wide range of characteristics and opportunities. And then I'm going to conclude by drawing the conclusion, are they our friend or are they our enemy, the versatility of these devices, and how we can go about dealing with that. So I'm guessing everybody knows this, but just to be sure, when we look at our computing systems, we look at memory and data storage, we actually have a pyramid of storage, and this pyramid is kind of built in function of the quantity of data that we can store, the speed of data that we can access, and the cost of the product that we are using. So if you look on the right side of my slide, you can actually see that on the top of the pyramid we have the computer chip, which is the fastest component that we would like to have, and closest to the computer chip we have the SRAMs, which are used to build cache memories. Now, if we go a bit lower down, we have higher density memories with lower speed, which would be the main memory in our system, which are based on the DRAM technology. And if we go even lower down on our pyramid, we have the data storage, which is either a flash if it's solid state, or a hard disk. So going down on the pyramid, we actually increase the capacity of what we can store, but also reduce a lot the speed of communication. As you can see on the table on the slide, when we look at the register and SRAMs or the cache levels, we talk about a very small number of cycles required to access the data stored on the device. And if we look at the main memory and even lower down on the flash drive, we see that we talk about hundreds of cycles, thousands of cycles of the CPU to access the data on our memory. So also you can see here that there is a mind the gap warning, which means that with increasing the with increased development in the CMOS technology, we actually managed to make better and better SRAM memories, faster, more compact, slower, with more capacity. We managed to do the same thing with the DRAMs, but there is a bit of a lag between how fast the SRAM can be and how fast the DRAM can be. So there is a speed gap in between the SRAM and DRAM, which we would like to cover, if possible, with the emerging technologies, and we will see if it's possible in a bit. And also we have a very big gap between speed and capacity between DRAM and the flash memory, which also we will need to see if we can cover it with these emerging technologies. Sorry. So if we look at these devices, I will try to show you which is their main issues and why we actually see limitations that maybe cannot be overthrown for these new technologies, old technologies, and try to see how new technologies can take the place. So if we look at the SRAM memory, the smallest, the simplest cell of the SRAM is the one that you can see here in the figure with the 6 transistors. We have a set of cross-coupled inverters and 2 access transistors that are controlling the access to the data in our SRAM memory. So this SRAM memory, it's actually the smallest or the fastest memory device that we have in our system. Because it is the fastest and it is large, we have 6 transistors, it needs to be as tightly packed as possible. So we actually design it with smaller than minimum size transistors in a very symmetrical layout, as you can see on the middle picture. And the problem is that because of this very tight integration and this struggle to make it as fast as possible with small transistors, we actually have a very big problem of process variability. So because there is a big problem in process variability, we need to make sure that our design is as symmetric as possible. And even such, we have the random variability, which makes the transistors within the memory cell itself very different. So this kind of brings a stability problem in the SRAM. So we might have problems reading data, we might lose the data stored, writing data, we might write wrong data. So we did a lot of testing and diagnosis around it in order to be sure that our SRAM works correctly. Now, if we go down on the pyramid, we go to the DRAM memory, which, as I have said, it is fast and it's compact, but it is much smaller than the SRAM memory because it only has 1 transistor and 1 capacitor. The data is stored in the storage capacitor, and it is a very fast and small device. However, it is not as fast as the SRAM since we need to load this storage capacitor. And the problem with the scaling down of the DRAM, it's actually the storage capacitor. Because as we scale down the technology, the capacitor becomes smaller and smaller, which means that the time that it is capable of keeping the data becomes smaller and smaller. So the problem with the DRAM, it's not only the fact that it is a bit slower than the SRAM, which is something that we can work with, but it is the fact that we need to refresh the data periodically to be sure that the data that was stored in the capacitor, it's refreshed and stays in the capacitor for as long as we need it. Now, with technology scaling, what we do in order to get high enough capacitance for data discrimination in between 1 and 0 logic in a DRAM memory, so in between loaded and unloaded capacitor, is the fact that with technology scaling, we decrease the capacitance, so it becomes harder and harder to discriminate. How the technologists have found to mitigate this problem is by building vertical capacitors. So we are actually digging trenches and building vertical capacitors. So you can imagine these are very thin, very tall structures, which actually pose problems with structural integrity. So we have big fabrication issues when it comes to DRAM because of these vertical structures that pose structural integrity and also are affected by process variability. Now, I have an issue with the slide. Yes, it's good. Now, if I go lower down in the memory hierarchy, I reach to the solid state devices, and as a good example of that is the flash memory. So we use the flash memory now for data storage because it is a very robust device. It is solid state, so it is embeddable in CMOS systems, and it is based on a floating gate transistor. This is a non-volatile device, so we can actually use it for data storage, but it is a very slow data storage device. So we cannot put this kind of flash memories up high in the hierarchy because that will slow down our operation systems. But we can use the flash as data storage non-volatile on the bottom of the hierarchy. And within the flash, it is one transistor, one floating gate transistor. So you can understand that the 1-bit storage, it's a small area. And on top of that, what we can do with the flash memories, because of this floating gate that can be filled either full with electrical charge or partially filled with electrical charge, we can actually have multiple level storage. So in the flash memory, we can have single level storage where either a full gate or an empty gate will give us the 0 and 1 logic, or we can have different levels of charge stored on the floating gate, which will lead us to multi-level cells. So we can have 2 3-bit level cells. Now, the problem with this is that with decreasing the feature size of our flash cells, we are actually increasing this variability around the nominal value. So with the technology scaling, we actually have problems discerning in between multi-level cell voltages. So we have problems reading the correct data in the flash. So to summarize, the biggest issue with the SRAM is the instability due to process variability, but also it has a very big leakage problem because the SRAM needs to have the power applied all the time not to lose the state. So it's a volatile device, needs to be supplied. So there is always a leakage current passing through our SRAMs. When we look at the DRAMs, the biggest problem is the structural integrity. As I have said, the vertical structures are very sensitive to fabrication. And also with DRAMs, we have the big problem of power consumption because we need to refresh a lot the data stored in the DRAM. And when we go to the flash memory, the biggest issue we have today is the data loss because of the variation in between the voltage levels of our flash. So we might have confusion between the data we are reading. And also with the flash, we have an endurance problem. We cannot write as much as we want on our flash. We are limited to about 10 to the power 5 cycles. So the flash is very good for continuous reading as a non-volatile device, but it is not that good for continuous writing like we need in the higher levels of hierarchy of the memory. Now, overall, the big problems with these technologies is the high variability, low dependability, large leakage power, and of course, the disparity between the speeds of memory and the CPU. Now, what we want to achieve with the new devices is to have small area memory. We need to have large endurance memory devices, if possible, non-volatile, so we can reduce the leakage. And we need to have speeds comparable to the CPU. When I say that we need to have very fast computation. Now, these things can be achieved with the emerging technologies, or we hope that they can be achieved with the emerging technologies. So there is a very, very wide variety of such technologies that can be used in order to attempt to solve these issues of CMOS and actually go to all the green points, all the good points of the memories that we are looking for. So this brings me to the second part of the talk, where I'm going to describe the new and improved RAMs, which are actually resistors. So the 3 main technologies being researched today for non-volatile resistive memory storage are the phase change memory, resistive RAM, and spin transfer torque. All of them have different structures, as you can see here. They are not identical devices, but what they do have in common is that they behave as a resistance, a variable resistance, and a non-volatile resistance. So with each of them, we can actually achieve different states of resistance that once set on our device, they stay there, and those states of resistance can be used for memory retention. How it works? So any one of these technologies can be replaced here in the blue rectangle as a storage element. And what we normally have, it's also an access device. This is to be sure that we are differentiating in between devices in a memory array. So this would be the simple structure of a memory cell with a resistive storage element. So we have our bit line and source line, our word line to control which word we are reading and writing to, and of course a sense amplifier. How they work is that the storage element can have different resistance states. So assuming it can only have two states, or we are only interested in two states, we would say that our device can have a low and a high resistive state, sometimes called also resistance on and resistance off. You will see later on why. And when we want to understand what's happening in this storage element, we read it with the sense amplifier, and the sense amplifier actually digitalizes this state and gives us a 0 and a logic 1. Based on a certain reference that we set on our system. So what is very important is that our sense amplifier manages to distinguish between high and low resistance by comparing it against a reference. So what is different between these technologies? So as I have said, they are very similar in that they are resistive devices. They are very different in that the ratio between the high and low resistance, it is very different from device to device. So when we look at the phase change memory, we can have a ratio at about 500. So it is a good discrimination between low and high resistance. A simple sense amplifier would suffice. When we look at the resistive RAM, we can have ranges from 100 to 1000 between resistance on and resistance off. Of course, there are many publications that are declaring much higher ratios between resistance on and resistance off. This would be an average value that I'm showing here, just to show that it is high enough, again, to be sensed with a simple sense amplifier. Whereas when we look at the magnetic devices, the resistance on, resistance off ratio, it's very low. So I'm reporting here 2 because it's one of the most commonly found value, but papers are, or research is reporting ratios as high as 6 or 7, but still we are under 10. So the design of the sense amplifier needs to be somewhat more complex in such a way to be able to reliably distinguish in between these two states, because of course these new technologies like the old have high process variability. So this is something that we need to keep in mind when we deal with these resistive devices. Now to go back and look at them and try to show you how they are written, because, well, here I'm showing you how they are read, so how we differentiate between on and off, but how they are written, it's a different story, and it's what actually differentiates them one from the other. The way we are changing the resistive state of our device, it's what makes them specific and different. So if we look at the phase change memory, we have a structure as such, where we have a top and the bottom electrode. Well, actually, we have a top and the bottom electrode in all of them with a specific material in between. So the phase change memory, we have top bottom electrode, which are metallic, and then we have a phase change material in the middle, which is actually doing the different conduction of our device. So if we look at the figure here on the top left, we can see that we have in blue the top electrode and bottom electrode, which are metallic, and we see from the bottom electrode there is metallic wire that goes up towards the phase change material. Well, this metallic wire is actually there for heating, so it has to be a very narrow and very long metal in such a way that passing high current through it will heat a lot the area above. So now the phase change material has the characteristic of changing phase, of course, so it can easily pass from crystalline to amorphous state. And this is what we take advantage of when we try to change state of the phase change memory. So we have this phase change material, we pass a current through the heating element, and this current hits the phase change material on top. Now, if it hits it enough, it can turn the crystalline state into an amorphous state. So you can see here on the chronogram on the right side, you can see how if you apply a very high temperature on the heating element, you manage to turn our device or our phase change material from crystalline to amorphous. Now, an amorphous device, an amorphous material has a very high conductive state because of the disarrangement of its structure. So when we put the switching region in the amorphous state, we actually increase the resistance of our device. This is called, in the case of phase change memory, reset. So the operation of putting the device in a high resistive state, it's called the reset operation. And as I have said, it is done with a very high temperature, which translates in a very high current passing through the heating element. And this current has to cause an increase in temperature in our phase change material such that the crystalline structure becomes amorphous. Now, another important thing is that we need to remove this current very fast from our system in such a way that the phase change material cools down very fast, and it cools down fast enough not to allow the material time to reorganize itself to the crystalline state. So what we have here is a very fast heating and a very fast cooling in such a way that our device stays in a crystalline state in reset, in an amorphous state in reset. Now, if we want to set the device, so we want to put it back to a low resistive state, what we want to do is to rechange the switching region from amorphous to crystalline. How we do that? We want to heat this material to a temperature high enough for converting from amorphous to crystalline, and keep the high temperature for long enough time in such a way that the crystallization, it is feasible. So as you can see on the chronogram here, we need very short and very steep pulses for the reset operation, for putting the device in amorphous state, and very long but lower amplitude pulses for setting the device, for putting it in crystalline state. So you can see here already that there is an asymmetry between writing high and low resistive state, and this asymmetry can be a problem when using these devices in real circuits, because, well, we are used from CMOS that programming a device either to 0 or 1, or storing the data in a memory either 0 or 1, takes the same amount of time and the same amount of energy. Where you can clearly see here for the phase change memory, this is not the case. Now, if we move back to the second kind of device, which is the resistive memory, there are many, many flavors of resistive memory, but they are all built in the same way, where they have two metal electrodes, which are marked in blue here, and an oxide in between, which is marked in a sort of orange in the figure. So what you see here is that we have a device which is pristine, so it has no conductance, it is an isolating device, it has a very high resistive, this device, pristine. And we want it to become low resistance. So we want to be able that in this device switch between low and high resistive states. So normally, or in some of the devices, not in all of them, many of the devices are being proposed every day where formation is not necessary. But in some of the devices, we observe the need of this formation, which means that we need to send an extremely high current through our pristine device to disarrange the structure in such a way that we can afford to have a conductive path in between the two metal electrodes. So you can see here in the second part of the figure, there is, it's called the on state, where you see the two metal electrodes, the oxide in between, and then these bubbles that go from the top to bottom electrode. These bubbles can be anything. They actually marked here as moving atoms. They are assuring the conductance in between the two metal electrodes. So if this conductance is being achieved, then we have a low resistive state. And then what we do, we apply an opposite polarity current or voltage, and we kind of disarrange these moving atoms. We send them back where they came from in the pristine state, and we decrease the conductance of this device, therefore increasing its resistance. So this is how we would reset the device. Also, as in the case of phase change memory, high resistive state means a reset device, whereas low resistive state means a set device. So as you can see here in the figure, in the third small representation, it's actually not all the moving atoms have gone back to where they came from, because we do not manage to make the device pristine again, but we manage to dislodge enough of them in such a way that we increase the resistance of the device, and then we can set it again by removing the atoms and making the connection in between the two terminals strong again. So you can see example representation of a voltage current characteristic of such a device. There are multiple types of devices with multiple types of characteristics. This one is actually a representation of the device that would only have two stable states, so it will behave like a bistable device. So we would have 1 and 0 easily achievable, and intermediate resistive states would be a little bit more complex. But as I have said, when we look at the resistive RAMs, we have a lot of protocols to create the on and off states. We have a lot of materials to combine to create the on and off states. So you can see here a table that shows not all, but the majority of the materials that can be used in memoristive devices. And you can see there is a very big combination of metals and corresponding binary oxides with which we can do the bistable resistive switching. So right here in this slide, you can see the great versatility of the resistive RAM, and you can imagine there is an extremely large number of memoristive devices proposed in literature today that need to be developed and investigated, such that we can maybe reduce the spectrum to the ones that are most useful per application. Now, if we go to the third memory that I'm presenting today, which is the magnetic RAM, the magnetic memory, it is also a three-terminal structure, a three-material structure. It has a free layer, a fixed layer, or the two metal layers, and an oxide in between. Now, the two layers, the free layer and fixed layer, are ferromagnetic layers. They have their own specific magnetic orientation. The difference is that the fixed layer, it's, well, as its name says, fixed. We cannot change it with an external field, or it has a fixed magnetic orientation, whereas the free layer, it has a free magnetic orientation. So we can apply a current or an external field in such a way that the orientation of the free layer changes from bottom to top, or from top to bottom. So you can see here the two possibilities of representations that we can have. We can have the free layer having the same magnetic orientation as the fixed layer, or the free layer having the opposite magnetic orientation as the fixed layer. In the first case, we say that the layers are in parallel state, and in the second case, we say that they are in anti-parallel state. Now, what we know about these devices, and when we pass current through them, is that if the two magnetic layers have the same magnetic orientation, then the current is passing, let's say, easily through the device. So we have a low resistive state. Whereas when the two layers are in anti-parallel orientation, we have the current passes more difficult through the two devices, so we have high resistive state. So you can see here in the middle figure the resistive voltage characteristic of such a device. It works in the sense of a hysteresis. It actually has only two stable states, the low and high resistive state, and it has an abrupt switch in between them. When we look at the way we are programming these devices are can be programmed in let's say two different ways. They can be programmed with very high amplitude and short pulses, which would be called the processional switching, in which we have a fast pass between low and high resistive states, or the other way around. And this processional switching, it's kind of seen as a deterministic switching. So once we apply a very high amplitude pulse with a very low duration, we know that our device has switched from one state to the other. We have another kind of switching, which is you see on the third figure at large pulse width. It is called thermal activation. This device is very, very dependent on temperature. So because it is based on magnetization orientation of these ferromagnetic devices, the temperature plays a very important role on how this magnetic orientation stays stable or not. So when we are in the thermal activation regime, we say that we are in a probabilistic switching regime. So actually we apply very long pulses, but with very, very low amplitudes, which says that our device will switch from low resistive state to high, or the other way around, with a certain probability which can be controlled. So you can see actually here in this switching probability curve, that depending on the pulse amplitude and the pulse duration, we can control the switching probability of the MTJ device, of the magnetic device. So this is a very important characteristic. It is yet another way to use these devices, and it kind of adds to the versatility of these technologies. So the magnetic RAM, it's actually a bistable device, but can actually have controllable stochasticity. Now, if we look at them and try to compare the three devices from the point of view of electrical characteristics and their use in a circuit, we see that they kind of have the same read access speed. So we are below 10 nanoseconds. We can even go below 1 nanoseconds, depending on the maturity of the technology we are using for phase change resistive or spin transfer torque. We have write access times that are not that comparable. I mean, the phase change memory, it's much slower in writing than the other two. It's also because the phase change memory requires a lot more time to be set than all the other devices. So actually the lag in write access comes from the set operation. The retention time is very good for the three technologies. Numbers reported to more than 10 years of retention in the three devices. Of course, depending on the maturity, we can go lower or higher than that. We have good endurance numbers reported in the literature, lower for the phase change, higher for the spin transfer torque, but overall, they are better than flash, and technology keeps improving in order to improve these numbers. And then the write energy per bit, it is also much larger in the phase change memory than in the other technologies, because of the fact that we need to heat up the element in such a way that it will write our data. Now, when we look into how they are switched and how we can use them, for the phase change memory, you have seen that there is a unipolar switching. So we need to use the same polarity current for switching to low resistance states and high resistance state. It has two-state storage, so it's like a bistable device in general, but it can also be used as multiple stage storage. How that can be done is by increasing the size of the programmable region, as you can see on the figure itself, the bubble, the mushroom that you see there. If we increase the size of the mushroom and we program only parts of it to amorphous, then we can actually have multiple stage storage in the phase change memory. So an analog-like behavior. When we look at the resistive RAM, it is mostly a bipolar switching device. You can also have resistive RAM with a unipolar switching, but most of them are bipolar switching, which means that you need opposite polarities for programming low and high resistive state. As I have shown you in the figure in the previous slide, you can have two-state storage, but also what is very important and cool about the resistive RAM is that it is able of multiple state storage. Most of the memristors of the resistive RAMs are allowing us to do multiple stage storage or even analog storage. So we can have an infinity of states between low and high resistive state. What is an issue here is, can we guarantee the stability of the analog states, and can we guarantee the repeatability of these analog states? Because the way the conductive paths are formed by using moving atoms actually gives us a lot of variability between every time a conductive path is formed or deformed. When we look at the spin transfer torque, as I have said, it is bipolar switching as well. So we need different polarity to switch from low to high resistive state. It is a two-state storage. It is bistable. Now, there are some structures of magnetic RAM with multiple layers of free ferromagnet that can do multiple bit storage, but the most of them and used today in architectures are 2-bit storage and 2-state storage, so the bistable, and they have the stochastic switching, which is very good for some applications, but it's extremely detrimental for other applications. Now, if we look at the main advantages of these technologies, we can see that the phase change is the most mature. It's actually, in phase change memories, we use the same technology as we used to use in CDs, only that it has been scaled down to nanoscale regime, and it is embeddable with CMOS, so it is not as a CD, but it's the same technology. It has proven performance, and it can allow multi-level storage. It has big reliability disturbance and high switching power issues, and it can be used as storage class memory or main memory. When we look at the STTM RAM, we know that it has high performance, it has very well understood physics, so it is very easy to, or relatively easy to see where we can improve the behavior of these devices and where we can work with materials to make them better. And the key challenges for the fabrication of these devices would be the patterning and etching and power stability trade-offs. So we can have very stable devices, but they will consume more power as respect to less stable devices, which could be faster and with less power consumption. They can be used in cache and main memory because they are the fastest of the three in terms of write operation. So some papers report the use of this STTM RAM in low-level caches. When we look at the resistive RAM, what we like about them is they are very simple and low cost. So they are the simplest of the structure. They can be embedded in high-density networks. They are using versatile materials and can be used in many applications, and they can allow for analog storage, which is very good for new applications such as in-memory computing or artificial intelligence accelerators. The key challenges when we talk about resistive RAM are the reliability and many failures due to the structure itself. The problem of stochastic switching, as I have said, because of the forming and deforming of the conductive ways in the resistive RAM. Based on moving atoms, there is a lot of stochasticity in the way they switch, and also some of them have the forming problem, which requires a lot of current applied to them. And they can be mostly used in memory in data storage. Now, when we look at the main issues of these devices, we say that for the phase change memory, the biggest issue is the large write current and the device scaling. So because it needs this heating region with the programmable area that needs to be reliable enough and distinguishable enough between two states, we have issues with device scaling. Also, we cannot put two devices too close to each other because of the cross-coupling temperature between writing one device and affecting the next. When we look at the STTM RAM, the biggest problem is the high current density and the integration density. So when we are writing the STT RAM, we need to use high current in order to switch reliably the resistive state of the device. As I have said, we do it with very short pulses, but very high pulses, in order to be deterministic in a way. And for the resistive RAM, the biggest problems are variability of switching, material selection, and endurance cycles. So depending on the type of resistive paths that we create in the resistive RAMs, we can have problems with its endurance. Now, if you look at the use of these devices, it has been They have been kind of sensed by YOL development in 2017, and new reports have came out. There are many industrial partners looking into their developments as embedded and standalone devices, and they are bringing them towards applications like for the standalone devices. We are looking into you can see here persistent memory, fast and reliable memory, code and data storage. So the way the industrial are actually predicting on how to use the phase change memory, magnetic RAM, and resistive RAM, and what is the predicted annual growth rate by YOL also is declared. So we can see that the prediction is that the phase change memory standalone are the ones that are going to take the lead, and then the resistive RAM and magnetic RAM will come right next. When we look at the embedded systems, or the way we can embed these devices in systems, we can use the non-volatile memories for analog ICs. You can see there is some market share for that. We can use them for ASICs, we can use them for memory, we can use them for edge computing, and there is a predicted growth of all these domains by 2027. So it actually shows this study of the technology. It shows that the fact that we are looking into these devices is not a waste of time. We are actually moving along. We are actually improving the way that we design systems, and the industrials are very interested in these new technologies. So I have shown you a little bit how they work. I have shown you a little bit that they are very different, but a lot the same. So now I would like to go towards their versatility, their usage, and how many facets they have, and if this is a good thing or a problem for us. So just to tell you that we have done a lot of development in time, with improvement in speed, dependability, power efficiency, size, and yield with the technology. So, but the CMOS is kind of predicted to reach a limit. However, we can expect some evolutions from the CMOS memory, but also evolutions from the emerging memory. We see that we are predicted to see more improvement in speed, dependability, and power efficiency with the emerging memories than with the CMOS. And why is because these emerging memories, as I have said, are very well researched today. And then there are new computing paradigms that take advantage of all the characteristics of these memories in such a way to take it to the next level. So if we look at the memories themselves, we have big challenges such as the shift from charge-based to resistive-based devices. So you can imagine there is a different way to conceive circuits. We don't look at charge anymore, we look at resistance. So first of all, we need to modify the way we think about the data. It's not a charge, but it's a resistance, but also the way we can manipulate the data. It's not only that change from charge to resistance that will, in theory, give us much more or reduce power consumption, but will also give us multiple usability of these devices. And which are the multiple usabilities are the emerging computing paradigms. So we can actually think about a modified memory hierarchy where the computation will be done in the memory itself instead of being done in the arithmetic logic unit. So kind of transporting the arithmetic logic unit towards the memory and embedding it in the memory. And also we would have ways of computing for artificial intelligence applications, not only accelerators for multiply accumulate functions, but also new neuromorphic computing paradigms, which are using computation within the device. So to show you a little bit more what I mean about that, so if we move from charge to resistance, we have the new materials and new integration techniques which are bringing a large versatility to these devices, but also from the point of the way we use them. We can use them for in-memory computing application, we can use them for storage, but also, as I have said, we can use them for neuromorphic computing. So this aspect of the versatility of our device, it is our friend, because it has so many facets, so many materials and integration techniques. We can actually do a lot of things with it, and we can use it in many applications much more much simpler than we would do with CMOS, with simpler circuits, less complexity, less power consumption. Now, if we look at all the applications that we can have with these devices, we can use them as discrete devices, or we can use them as crossbar arrays. We can use them as analog devices or digital devices. And all of these applications, well, this is just a very short snippet of what we can actually have in the application, and new applications are being proposed every day. But you can see that we can kind of classify them in three big classes, which would be the normally off computing, the computing in memory, and security applications. So these are all very good and very great advantages of the device versatility. However, unfortunately, all these devices have a problem of stochasticity. So as I have said, for the magnetic RAM, it is the switching process itself, it's stochastic in nature if we control well the control signals. The resistive switching, it is stochastic in nature because we have a movement of atoms that it's never the same the second time we apply it. So this stochasticity, it is very good for neuromorphic circuits, for because there are proposals that are based on the stochasticity of the device in order to train much more efficiently artificial intelligence. There are proposals for in-memory computing with stochastic devices, which are moving us towards the approximate computing realm and give us the opportunity of reducing power consumption. And the stochasticity, it's very good for security primitives because we can build random numbers in hardware with intrinsic stochasticity. Now, unfortunately, this stochasticity is very bad for computing in memory, for security primitives like physically unclonable functions. They are very bad for normally off computing. They are kind of very bad for wherever we want to be sure of the data stored in our device. So the fact that they are stochastic, it brings a lot of advantages, but it actually brings a lot of problems where we don't want them to be stochastic, where we need a deterministic behavior. So from that perspective, they are kind of our enemies. Now, if we look at applications beyond the memory, we can, as I have said, use devices in logic in memory computing, analog or digital, neuromorphic computing, or in hardware trust for physically unclonable functions and TRNGs. So I'm not going to go into details with these applications. I'm just going to show you what are the big problems with these applications. So if we look at the computing, in-memory computing, which can be done digitally, one of the most researched solution in memory computing is the one based on scouting logic. This solution is very briefly summarized here, where you have in a memory array, it's just a snippet of a memory array here, where you have M1 and M2 are the memory cells that are being read in the sense amplifier. So if you read cell by cell, you have the normal memory operation. Whereas if you read multiple lines at the same time and you modify a little bit the sense amplifier, you manage to do logic operation like OR and XOR and their opposites. So what is the problem here is that when you do read operation, well, you have a distribution of resistance low state, resistance high state. So when you do a read operation, you kind of compare with the reference. If this distribution, it's not very wide, we can easily differentiate in between read and write, between low and high resistive state. So this is something very good for us. We can manage to have this correct read operation in most of the devices. However, if we do logic operation, we risk to have a problem of discerning in between states, as you can see in this bottom figure, where the distribution for combination of resistance high and low can actually be widened because of the combination of the two devices. So then you could have problems when reading, instead of performing an OR operation, you are performing an AND operation, for instance, or you are getting the wrong result of your OR operation. Now, another very researched solution for this in-memory computing is the one that you can see on the right side of the screen, which is the magic operation, which is everything done within the array, as opposite to the one I just explained, where the output of the operation is registered by the sense amplifier and output as a voltage. When you look at the other proposal, which is on the right, the output of the computation is actually registered as a resistance within the array. So this is actually called the magic logic, and you can see doing different voltage and duration sweeps, you can actually have a very wide range of operations where voltage and durations where your device works correctly. However, if you modify a little bit this control and you go to another logic which is called Felix, and it's actually doing the same thing with a different set of operation conditions, you see on the right hand side that the states are marked in purple. The correct states are marked in purple. Everything that is not purple in these two figures, it is either loss in input data or an incorrect operation. You can see that the purple region from the NOR operation actually decreases a lot when you do NAND operation, and you actually do them in the same way. So the process variability and the way we control the system becomes very, very problematic when we try to do more complex operation like Felix NAND or even XOR on the Felix. So we have a big problem here. Let's say we need to fix the problem of discrimination between logic states, the strength of the logic states, and the process variability. So the versatility is very good because it gives us a very good application in digital in-memory computing, but there are many issues that need to be solved. When we look at the analog computation, there is a lot of research going on how to accelerate the artificial intelligence systems by accelerating the multiply accumulate operation, and it is normally done with memoristive arrays where you use one memoristor as a synapse, which is the G in the bottom figure, and then the voltage that controls this G, the conductance of the resistance, it's applied as a read operation. Now, as you can see, just by applying the Kirchhoff law, you get the current, which is the multiplication between voltage and conductance, and the sum of currents, that is the multiply accumulate operation. So you can do that with analog devices. Also with analog devices, you can do neuromorphic computing, which is something very researched also today for spiking neural networks for bio-inspired computations. Now, if we look at this bio-inspired computation and look at the synapses that you can obtain with different levels of conductance in a stochastic regime, we have shown that there is the behavior of the synapse is very highly affected by the voltage that you apply to it or by the temperature of operation, which can cause a lot of variability in your accuracy. So here you can see an example of the variation of the spiking neural network recognition rate, where you have different defects or faults on your synapse, which kind of coincide with different levels of conductance that you can achieve with your device. So the problem here is also that you have process variability. There is a big problem with reproducibility, the stochasticity, which is very good if we look at spiking neural networks, which are probabilistic learning, but it is very, very bad if we look at normal Mac accelerators. And I'm going to finish my presentation with a small overview of what happens in hardware trust applications. We can use these devices as physically unclonable functions where you generate signatures for hardware where they are placed. These signatures are unique in nature and they cannot be reproduced because they are based on process variability of your devices. However, these signatures can be affected by temperature and voltage variation, by aging, and by the stochasticity of the devices. Another thing that you can do and take advantage of the stochasticity of the devices is to build true random number generators. Now, as I have said, the MTJ, the magnetic element, it's by nature a stochastic device. So you can see here on the middle figure, it's actually the oscillation of our device around the two stable states. So if you control it correctly, you can get high entropy number, a 50-50% of being 1 and 0. However, if you have a lot of variability, which you do have in your system, process variability, voltage variability, temperature variability, you can, instead of having 50% probability of switching, which would give you the highest level of entropy, you are actually varying in between very wide ranges of probability, which will give you a very bad quality random number. So you need to take care of this variability when you talk about TRNGs, temperature and voltage and process variability, in such a way that you can fix this. So to conclude, are they good or bad, these devices and their versatility? Well, actually, there are many reasons not to use emerging technology RAMs. And those reasons are, most of them related to the CMOS and the fact that we know CMOS and we know how to use it and we know how it works and it's cheap and we have known architecture and we have easy manufacturing test and it is safe and it's inexpensive. And also reasons not to use emerging technology RAMs are intrinsic to them because there is a very wide area of emerging technology exploration. So it is very expensive to go through all of them and find a good one. They have challenging operation modes, as you have seen. You can have them as bistable devices, but you always have some either stochasticity or variability issues that would make you work a lot on the way you design your systems. They also need unconventional testing because they are different devices with different characteristics, with different kind of defects and faults. So they need different kind of testing that would cost a lot. And also you would need to renovate the fabs because, well, you need to include these new devices in old fabs or build fabs for them. However, there are reasons to use these devices, which also come from the CMOS technology. Like there is a technology wall, so we are reaching the limit of the CMOS. We are reaching the limit of how fast we can go with the CMOS. There are exotic applications that cannot be reliably designed with CMOS technologies, like in memory computing and accelerators for neural networks. And we have the need for ultra low power, so it is they are extremely efficient in normally off computing. Now, if we put all these things together, you can see that many things are repeating, like wide area of exploration. It is a pro and a con because we have a lot of devices and we have a lot of versatility in their use. So I would like anyway to conclude that they are our friend, that the pros are actually overweighting the cons. I'm guessing it's not a surprise you are expecting this conclusion from my side. And I would also like to conclude that given their versatility, the number of materials that can be used, the number of operation modes in which they can be used, and architecture designs that can be approached with these new devices, it is very likely or very unlikely that we will reach an equilibrium like with CMOS to have a single technology good for all. It is very likely that will be multiple technologies good for something. So with this, I would like to thank you all for listening to me, and I will take questions now. Thank you.
So thank you very much, Ioana. So we have here some questions for you. First one by Enrique Hansen. So he has a question concerning the second type of RAM we were covering. How do we manage the heat dissipation of a storage cell only to stay close to the respective cell and not affecting adherent cells?
Thank you for the question. I'm guessing you are referring to phase change devices where we have the heating element within the cell. So what happens in this case is that the heating element, it is encased in an isolator. So it is very localized heating because we have a very narrow metal wire that passes current through it. This being said, it is not that localized. We have cross-contamination, so it is one of the biggest issue with phase change devices is to place them as far as possible, not to have cross-contamination during writing, but as close as possible to still have high integration capabilities.
Thank you. So we have now a question by Thiago Hanaboth. For ReRAMs, which require formation step, is area overhead of the charge pump circuit relevant?
before that, it is much more relevant, the area overhead of the access device. So yes, it is, because you need to pass a lot of current through it, so you need high voltage for that operation. But unfortunately, the largest cost we pay for this is the transistor that you use as an access device, because that transistor needs to allow a lot of current. So instead of being able to use a minimum size transistor, for instance, on a 28 nanometer technology, we need to use a 10x wide transistor for enough current for the forming. Unfortunately. Fortunately, there are many devices now being researched to remove the forming process. I mean, they are built with materials that do not require forming. That's one thing. And another thing, there are other ways of doing forming which are from the outside, like laser injections, in order to form the device without the need of high current from the circuit itself. Because it's a one-time operation, you can do it from before sending it into the market.
Thank you. So now a question by Caroline Garcia. There was a mention of the reliability issues of ReRAMs. In the case of noise, especially random telegraph noise, what approaches are being studied to deal with this issue?
So yes, there is a very big problem with ReRAMs and the random telegraph noise, which is being studied now. So I would not have approaches to give you to mitigate this issue, but I would have to tell you that there is a lot of study going on what happens with basically the stochasticity cycle to cycle, the variability cycle to cycle of the device. It is caused by the moving atoms and by this random telegraph noise. So we know it exists, we know it affects devices. There are many studies working on how exactly the devices are affected and how exactly this random telegraph noise effect can be modeled into the device, so then we can actually do circuit simulations and see how we can deal with them.
Thank you. Now a second question by Thiago Both. Reliability-wise, what are common reruns faults? Apparently, they are currently offered by TSMC in 14 nanometers node. What are typical applications?
So for the resistive RAM, as I have said, there are many technologies and each one with its specific reliability issue. But what is common to all would be a resistance drift. So what happens is that at young age, you would have a good discrimination between high and low resistive states if you work in digital, for instance. But then with time, with an increased number of operation on this device, you would actually drift your resistive states towards each other. It's mostly drifting the low resistive states toward the high. So it's a more of a deterioration of the low resistive state than the high resistive state. And it actually, it is the main problem with these resistive RAM devices, reliability wise. Typical applications, as I have said, memory wise, we see them if you talk about a memory array. So build a memory array with these resistive RAM, so you can use them directly as main memory. You could use them as accelerators for in-memory computing, as I have said, for artificial intelligence. As I have said, one of the most researched applications for resistive RAMs is the acceleration of multiply accumulates, because you can do them only by Kirchhoff law, so it is very easy, cheap, but they come with a very high cost of analog to digital converters. Now, if we use them as discrete devices, you can use them in non-volatile logic, for instance, for power for normally off computing. So you can build digital logic gates with non-volatile latch. So after you did the computation, the data stays there, and when you power your system, you have the data of the last operation stored in your non-volatile devices.
Thank you. So I see no more questions in the chat channel, but so I have one for you.
Yeah.
Anna. So as you know, one of the directions in implementation of memories nowadays is the use of 3D memories. In one hand, using TSV, in another one, monolithic ones. So, do you have some information about also the research on the 3D memories for Emergent memories technologies?
So yeah, thanks for the question. I would say they are already 3D because they are built on top of silicon. So you have your CMOS whatever circuitry on bottom, then you have 2 3 metal layers, and then you have your memory devices. So it's kind of already 3D within in back end of line. That's it. For now, that's what I can tell you. There are already discussions of stacking them up.
Yeah.
But with the new technology, with the new materials, sometimes there is a problem of thermal management that not always can be overlooked. So the temperature at which we need to deposit these devices, and then the temperature at which you would need to deposit your top chip would actually affect their functionalities.
Okay. So thank you very much, Ioana, for this very nice, interesting talk on a hot topic nowadays. So
Thank you
thank you
again for
very much.
inviting me. It was a pleasure.
I hope to see you in person in a near future.